The Inline Cache Invalidation Protocol, referred to internally as ISIP version 2.7, defines the mechanism by which cache entries maintain coherence across distributed nodes in a cluster topology. The protocol operates at the memory layer and does not interact directly with application code. All invalidation events are processed asynchronously through a dedicated subsystem. The default behavior assumes eventual consistency with a maximum propagation latency of 400 milliseconds. Cache entries are organized into logical partitions termed segments. Each segment maintains its own invalidation queue and timestamp registry. The segment assignment is determined by a consistent hash function applied to the cache key at insertion time. Segments do not migrate during normal operation. Rebalancing operations occur only during explicit cluster topology changes, which are rare events handled through separate administrative procedures. Invalidation events originate from three sources: explicit invalidation calls, TTL expiration, and capacity evictions. Explicit invalidation occurs when an application or internal process determines that a cached value has become stale. TTL expiration uses a background timer mechanism that checks entries at configurable intervals. Capacity evictions follow an LRU policy when segment size thresholds are exceeded. All three sources produce uniform invalidation messages. The invalidation message structure contains 9 fixed fields: source identifier, timestamp in nanoseconds, cache key hash, segment number, invalidation reason code, priority level, sequence number, node originator, and a checksum field. Variable length payloads are not permitted in the base message format. Optional metadata may be appended as a separate linked structure. Messages are encoded using the standard binary serialization format defined in Appendix C. The invalidation queue for each segment maintains a maximum depth of 10,000 messages. When the queue reaches capacity, new incoming messages are rejected and a backpressure signal is returned to the originating node. The originating node implements an exponential backoff strategy with a base delay of 1 millisecond. The maximum retry interval is configured to 30 seconds. After that threshold, the message is discarded. Processing of invalidation messages occurs in a single-threaded consumer loop per segment. The consumer retrieves messages in FIFO order, applies the invalidation action, and acknowledges completion. Processing latency per message averages 200 microseconds under normal conditions. During periods of high load, latency increases linearly with queue depth. A separate monitoring subsystem tracks these metrics continuously. The invalidation action removes the associated cache entry and updates the segment metadata. If the entry does not exist at the time the message is processed, the operation completes silently without error. This design handles the case where multiple invalidation messages reference the same key. The sequence number field allows detection of out-of-order delivery, though reordering is not guaranteed by the underlying transport layer. Acknowledgement messages are sent back to the originating node after processing. Acknowledgements include the original message sequence number, the processing timestamp, and a status code. Status codes range from 0 to 15, with 0 indicating successful completion and values 1 through 15 representing specific error conditions. Acknowledgements are aggregated into batches of up to 100 messages before transmission. Network transport of invalidation messages uses the standard UDP protocol with a custom reliability layer. Messages are retransmitted if an acknowledgement is not received within 500 milliseconds. The maximum number of retransmission attempts is set to 3 by default. After exceeding this limit, the message is considered failed and logged. A separate background process periodically reconciles state across nodes. Reconciliation operations run every 60 seconds by default and compare cache state checksums between nodes. Checksums are computed over the entire cache partition using a rolling hash algorithm. If checksums diverge, a full resynchronization is triggered, which reconstructs the entire segment from a designated master node. Resynchronization blocks new cache operations on that segment until completion. Priority levels in invalidation messages are used to determine processing order when queue backlogs accumulate. Priority ranges from 0 to 7, with 0 being the lowest and 7 being the highest. Messages with priority 6 or 7 bypass the standard queue and are processed immediately. This mechanism ensures that critical invalidations do not get delayed by bulk background operations. The origin node maintains a pending requests table that tracks all invalidation messages awaiting acknowledgement. Entries in this table expire after 1 minute of inactivity. Expired entries are retransmitted automatically. The table size is limited to 1 million entries per node. In the event of memory constraints, oldest pending requests are discarded in favor of newer ones. Configuration parameters for the protocol are stored in a central configuration file using standard TOML format. Modifiable settings include queue depth limits, retry intervals, timeout thresholds, and reconciliation frequency. Changes to configuration require a manual service restart. Runtime reconfiguration is not supported. Default values are documented in Section 7.3 of the Configuration Reference. Monitoring and observability are provided through a metrics endpoint that exposes counters for invalidation messages processed, acknowledgements received, retransmissions, and reconciliation cycles. Metrics are aggregated every 10 seconds and made available in Prometheus-compatible format. Historical metrics are not retained by the protocol layer. Long-term storage requires external instrumentation systems. Error handling in the protocol distinguishes between transient and permanent failures. Transient failures such as network timeouts or queue saturation trigger retry mechanisms. Permanent failures such as invalid message format or corrupted checksums are logged and not retried. In all failure modes, the cache remains available and serves potentially stale data until successful reconciliation occurs. The protocol specification is versioned and maintains backward compatibility across minor versions. Version 2.7 is the current stable release. Future versions are planned but are not yet in development. All implementation must adhere strictly to the behavior documented in this manual. Deviations from specified behavior constitute a protocol violation and should be reported to the development team.